So, again, talking about a turbine, hopefully that gets you some basic idea of what this is. A steam, or this is kind of a cross-section, some steam turbines that we might see in a nuclear power plant or a coal-fired power plant. You could use a solar collector to heat up water and boil it off, and whatever your heat source is, you could generate steam, run through basically these high-speed spinning discs of aluminum, get those to spin, and then you hook up to the spinning shaft, whatever you want to hook up to it, most likely an electrical generator, but something. Okay? So you have high energy fluid coming in, you allow that fluid to kind of expand. As it expands, remember, and when we talked about boundary work, we said as a system expands, it's doing work out to the surroundings. Same thing here. As you allow this high pressure, high energy steam, or whatever fluid, could be air, could be R134, there's some issues with that, but most likely we're going to use steam for a number of reasons. Air, that's water vapor. So you have high pressure, high temperature water vapor, and you allow it to expand as it moves through. As it expands, it's going to push energy out, and also you're going to have kind of a combination of both kinetic energy and enthalpy are being converted to this power output, and that's the purpose of a turbine. Could have heat in both cases, and it's not uncommon given all the conditions. They want you to estimate the heat transfer for these devices. Could have a kinetic energy change for either one of them. Okay. Just depends. Couple more devices we may encounter. And so a couple more devices we might encounter. Multi-inlet and multi-outlet devices. Heat exchangers and mixers. So a mixer is a device that has more inputs than outlets, basically. That's pretty straightforward. Heat exchanger is a device that's typically what a heat exchanger will have is it'll have a hot stream and a cold stream. So you'll have hot fluid coming in one end, cooler fluid coming in another end, and then those fluids normally in a heat exchanger, normally they do not mix. Normally they stay separated. And one is used to cool the other, one is used to heat the other. It's the two fluid streams exchange heat. It's a heat exchanger. The radiator in your car, if you ever looked at that, it's this device that's designed to keep your engine cool. So the radiator has hot fluid coming out of your engine, and that fluid then flows through kind of an array of aluminum fins that you pull air through. And so the air is the cold stream in your radiator, and the radiator fluid coming out of your engine, you cool it down, and going back into the engine to be heated back up. That's the hot stream. So in a radiator within your car, your cold stream is the air from the outside, and the hot stream is the radiator fluid coming from your engine. Just one example. And there's quite a few examples we could point to. Okay. If we're looking at the heat exchanger, because again the two streams don't mix, so you can treat each individual stream as its own system, where heat goes out of the hot stream and into the cold stream. So you have two different control volumes exchanging, where they both have a heat transfer value, and that heat transfer is the same between them. It links them together. Or you just draw one big system where you've got two mass ins and two mass outs, and we solve for the unknown quantity, whatever it is we're looking for. So I think there's a heat exchanger example. Yeah, so what we've got in here, I've got just a bunch of example problems that I pulled from various versions of this textbook and other textbooks over the years, and I think I've got 4 of them in here, and there's worked solutions in the PowerPoints available on Canvas. So you have worked examples plus the examples in your text plus whatever you can find on the internet. The hope is you've got various resources to, when you actually go to solve these problems, various opportunities to look at that. But let's solve a couple of these examples, okay? So I've got a steam turbine here. This is, you would find a problem like this somewhere in the 540s to 560s in the Changel and Bowles text. I don't know if this problem this used to be a problem in the 550s, and I got tired of trying to figure out which problem number it is because I've taught from multiple editions of this text. So I just say it's a problem in the 550s. Oh, by the way, before we start examples, one last thing I might mention. Right, you also, again, you have heat exchangers and mixers. Right? In all cases, set this aside so I can write. In all cases of control volumes, what we're going to find is that the change in enthalpy from the inlet to the outlet is going to be much, 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 much greater than the change in potential energy. Now what that means is typically we're going to assume that there's a negligible change in potential energy. Okay? So typically we're just going to assume, because this is going to be on the order of kilojoules, and this is probably going to be on the order of microjoules. So if I include it in the analysis, the change in potential energy is probably only going to affect maybe the 9th or 10th significant figure. It's not going to matter. Now the change in kinetic energy might be joules, where the change in enthalpy is kilojoules. So it might be large enough, the change in kinetic energy might be large enough that we need to consider it, especially in these devices. For sure, nozzles and diffusers, we have to consider a change in kinetic energy. Okay? So I guess while I'm finishing up this video, let me see if I can squeeze one more thing in here. So we're normally going to neglect the potential energy. Should we consider the change in kinetic energy? Well, is it a nozzle or diffuser? Right? If it's a nozzle or diffuser, yes, you have to nozzler. I put the R here, but I didn't put it there. Is it a nozzle or diffuser? If the answer is yes, then yes, you have to consider the change in kinetic energy. Question number 2. Did they ask for one of the speeds? Does the problem ask for one of the speeds, either at the inlet or the outlet? If the answer is yes, then yes, you need to consider the change in kinetic energy. Question number 3 is, question number 3 is, are the speeds given? In the givens, did they give you the speeds at the inlet or the outlet? Okay? So, and then the 4th thing is, can you find the speeds? Right? And normally that's going to be AV over the specific volume is equal to the density, AV, which is equal to m dot. So basically this is kind of the best tool you're going to have to find a speed if you know the area at the inlet and or the outlet, and if you can find the specific volume or density, to find the mass flow rate, or given the mass flow rate, find these other things. If you can find the speeds, and this is not the only tool you could use to find the speeds, but it's the most common tool to find the speeds. So again, ask yourself these questions. And if it's no to all 4, then assume that V1 is approximately V2, or at least you're assuming that the change in kinetic energy is negligible. Okay? So that's kind of what you got. And why is that important too? What the heck does this matter? Well, remember, you've got to quantify the energy of the mass in and the energy of the mass out. The energy of the mass in and the energy of the mass out. Well, the energy of the mass is going to have its own enthalpy, its own kinetic energy, and its own potential energy. And here I'm saying, look, you most likely are just going to assume that the Z values are negligible. Okay, the change in potential energy, right? Most of the time we're just going to assume that the change in potential energy is negligible. Okay? Now what about the kinetic energy? Do we need to quantify that change in kinetic energy? Well, it might be big enough that we need to quantify it. In the case of a nozzle or diffuser, yes, we have to quantify the change in kinetic energy. That's given. That's just the purpose of those devices. Their purpose is to change the kinetic energy. Are they asking for the speed? Okay, well that means we're going to have to figure out speed somehow, and the first law might lend itself to doing that. Did they give you the speeds? If they give you the speeds, then it's just easy. Just plug it in these here, and it might be insignificant compared to the change in enthalpy, but you've got the information. Go ahead and use it. Can you find the speeds? Right? And again, conservation of mass is most likely your best friend there. If all four of those is no, then let's just assume the kinetic energy change is negligible. Okay? How am I on time? All right. I'm going to stop there. Right? I'm going to stop this video there, and we'll pick up the example problem in the next video.